Okay, we're looking at the Synchronous Motor Lab, and what we have here is we have our resistive load connected to the output of our 232, which in this case is our generator, and our generator, of course, we have that load connected across A1 and A2, which is the armature windings. We have this connected for long shunt. I have a drawing on the board here showing you what a long shunt generator should look like, or cumulative compound rather long shunt. So the idea being is that your series and your armature winding are connected in series. And so the key here is the very first thing when you fire this thing up, you need to make sure that you're getting a voltage at your output. So we have a couple of voltmeters here. So I have a voltmeter that's going to measure our generator voltage. I also have an amp meter set up to measure our field current. Now that's not the field current of the generator, but the field current of our synchronous motor. So down here you can see we have we're hooked up to the field, and we're going to be altering that field by altering the rheostat and providing more voltage, causing more current to flow from our power supply. So as we increase field current, we're going to be increasing the strength of the magnetic field in the which is rotating on the rotor, and that's going to strengthen that bond between that and the rotating field in the stator. So we have also an inductive load hooked up here. That inductive load, when you start it up, you're only going to have on, once you know that everything's running, you're only going to have on about 30 watts or 30 VARs rather per phase, and you're going to have all of your resistive load off. Now the resistive load, again, that's coming off of your generator. Your inductive load actually comes to the line side of your starter. So you can see that right here we have our leads coming from, our three-phase leads coming from the line side of our starter. Now this is where we're going to hook up the circuit analyzer, and that's going to tell us the power factor of the system. If we want to know the power factor of the load, you have to hook up the amp clamp over here on the motor, and that's part of the lab, is it's going to switch you back and forth. Okay, so the first thing we're going to do is we're going to fire this up. And we're going to make sure that we have 120 volts output at our generator. So that's this guy here. If you're not generating a voltage, your lab isn't going to work correctly. So I have changed the field on the generator to make sure that we have an output of 120 volts. It then calls for the field on the synchronous motor to be putting out 300 amps or 300 milliamps rather of field current. So I'm going to just adjust that slightly, and we're going to do that over here on the rheostat until we reach about 300. That's pretty darn close right there. And at this point we have 694 milliamps of armature current coming from the synchronous motor. So the idea being here is that our motor, there's not much load. You'll notice on the fish scale I have the correct direction. That's the other thing you have to check when you get this thing going. That fish scale has to go down. If you have if your synchronous motor is turning in the wrong direction here, you not only will build down, but you won't get the fish scale moving in the right direction. So we're sitting at about 2 newtons right now, and the next goal then is to apply 6 newtons by increasing the resistance that we have connected to our armature windings here. So we're going to come over here and we're going to turn on, and in this case it actually turns out to be the entire resistive load bank. And we'll come back over here and you can see that we are at even just a little bit more than 6 newtons. We could maybe take a little bit off, a little bit more. There, we're bang on 6 newtons right there. So it looks like we actually needed, let's see, 30 and 60, about 90 per phase. Of course, this is single phase coming from your generator. Right now we are actually overloading at 1.2. So the next goal then on the lab, it calls for us to take a reading of the power factor. Now as you can see, my power factor is 0.64. That's not great. So then it says let's adjust the field current, creating that stronger bond, and bring that up to 0.9. So we're going to come over here to the rheostat and we're going to adjust that till we read 0.9. Now it takes time for this thing to change, so don't, like I'm turning it takes 3 or 4 seconds for your meter to actually start picking up the improved power factor here. So if it doesn't change right away, don't assume that you have a wrong connection. Continue to move this. This is taking some time, but you have to take your time with it. So we're pretty done. There we are, 0.9. Now, our actual armature current went down because we created that stronger bond from the previous experiment. You will recall that. We're now operating under the full load current. Our full load current here is about 830 milliamps. Now the question is, how much field current did we have to add in order to provide that? And you can see that our field current went up from 300 in this case to 584 milliamps, and that improved our power factor to that 0.9. Now the next part of the load, it says turn on an additional 270 VARs. That's approximately 60 per phase, so we're going to turn on some more inductive load, and we're going to see what that does to our power factor. Again, be patient, wait for it to climb all the way down here. So that dropped it to 0.73. So the next move then, of course, is to make sure that we correct this back to 0.9, which is what we will do next. Now, when we talk about power factor, you guys, it's PF, not DPF. So that's about where we're at. Now, what did that do to field current? Take a look at our field current. Had to go up a whole bunch more. Okay, the next thing it says, hey, let's check out the motor and see what power factor we have on the motor. So what we're going to do is we're going to move the clamp, and I might add, if you look at the clamp, right down you can see that there's an arrow right in the jaws there, and it talks about which way the arrow has to go. So we're going to come over here, and we're going to put this on one of the motor leads with the motor facing the arrow. So we're going to go like this, motor's facing the arrow. And we're going to see what our power factor is at on the motor over here. Now it's saying 0.71. So you can see that our not only have we improved the power factor here to 0.9 on the system, but we've improved the power factor to the motor, 0.71. Now it says let's add a little bit more inductive load, so we're going to add an extra 15 per. Now we have to, if we want to carry on with this lab, we have to make sure we come back and put this on the service. Okay, so we're on the service now, and you can see that our power factor, because of the extra inductive load, has dropped. So it says now let's correct it to 0.9. So again, we go back to our rheostat, and we're going to adjust this until we get 0.9. Okay, we're at 0.9. So as you can see, our motor current is actually, we're still overloading it a little bit, but look at what we had to do to field current to bring that back up to that power factor. Now if we move our clamp to see what that did to our motor, so we're going to put that clamp back on. Let's see what that did to our power factor. So once again, it improved the power factor. You can see that the motor power factor improved, which by improving that improved the power factor of the entire circuit. That's it in a nutshell.